So, like, first, I'll a little bit introduce myself, like, in very short.
Hmm.
So, I work as a principal data scientist with a company called Ehol Delhaize. They are a
Okay.
supermarket here in Holland. And I have, like, I'm not a data scientist by education. I did my computer
Hmm.
science engineering and then some masters and then MBA. But, like, I have a nose for data somehow.
Yeah.
So, jumped to this field, and since then, I've stayed here for like 10 years. And I was really very happy to discover your podcast because you bring refreshing perspective, especially when you criticize those papers. I love it.
Hmm.
So that's the first thing I want to start with. So the current direction of research, what do you think? Like, is it in the right direction, or something is missing? I have my own like ways to look at it, but please.
Hmm. Yeah, it's. I think it's easy to be overly cynical as well. So it's easy to fall into the trap of criticizing everything because it's easy, right? Like criticizing is often mo- a lot easier than um, highlighting good things. I mean, of course, there's marketing and all, but I definitely don't want to fall into the trap of just criticizing everything all the time. Now, that being said, there is stuff to criticize in the field, and there's a lot of things that are missing. So, in machine learning, I think it's not a secret that there is a sort of a hype right now. Maybe it's fading off a little bit, but in the last 4 or 5 years or so, there has been this really big boom in people trying to get into the machine learning field, um, in universities expanding their departments to include more and more machine learning, but also machine learning going into other departments. Like it's a lot of departments that are maybe not even computer science now are also dominated by machine learning because people use it, people apply it to their own problems. So there is this hype, this increase in attention, and bringing with it a influx of new researchers, an influx of new papers, and sort of a publication pressure with it. So there's a lot of people wanting to publish a lot of papers, and the amount of stuff to be discovered, on the other hand, hasn't increased by as much. Therefore, we've seen a lot of papers that are a lot of research that is essentially, well, worthless a little bit. Like new techniques coming out that work on a particular data set in a particular setting. If you butcher the baselines to make yours stand out a little bit, but then if you try to apply it somewhere, just doesn't work. So I think the gut reaction immediately of people is to sort of distrust many of the papers they read, distrust new research until it is sort of verified by many different sources and so on, which is, I think, a good approach. But it's different, I guess, than in other scientific fields where a published paper has some sort of a weight behind it, right? Is, oh, this has been through peer review. It's esteemed professor such and such has, is on the paper. That's just not the case anymore right now in machine learning. And I think, yeah, that is worthy of criticism. Though it's a bit of a, I don't know, don't hate the player, hate the game. So it's just of a fact that there is this big hype in the field, and I don't like. I have some ideas of how to cope with it better, but I think it was almost unavoidable given that the field has exploded. So that, to me, what's missing in the field is a bit more of a, let's say, a return to, not maybe a return, but a bit more of an understanding that most of results that we find are kind of shaky, um, which we inside of the field already do, but maybe not people outside. And also, a little bit of I think, more diversity in directions of research because we've sort of converged more and more to, let's say, I apply neural networks with gradient descent and either supervised or self-supervised learning to some problem. And it seems like as a field we've sort of very narrowed down our interests, and there's a lot more things in machine learning and AI in more general that have a bit been forgotten, and I'm waiting for them to come back. I'm waiting for evolutionary algorithms and in part symbolic AI and whatnot, all of this kind of stuff to sort of come back with sort of clever algorithm or a new technique that makes them just fast enough to compete and augment what we have right now.
Yeah,
So that's a bit of a, yeah.
no, I agree. And but like I was actually one of those guys who got caught in this AI hype, and
Mm-hmm.
because then
Yeah,
I
me
was
too.
so like then it was a different problem for me because I thought that everything is critical and I have to understand everything. I took the other way
Mm-hmm.
that nothing should be criticized. It's my fault that I don't understand these things. But then over the time, I realized that hey, if a paper like imagines its own lemma, then takes a data set and then tweaks it to suit that lemma, and then says, hey, we are better by 0.02% on this baseline. What can, what can you do with that model?
Yeah, I mean there is legitimate research where you say, okay, we create our idealized data set for a particular scenario to really showcase, our method works or something like that. This is all fine, but I think the field also has forced everyone to say your idea has to fit exactly 8 pages, right? This sort of, we have come to this agreement of, okay, 8 pages is what you need to for one unit of research, and also if it's not state of the art on something, it doesn't matter, and it has to have some complicated math in it. Otherwise it's no good, and recently it has to have some fancy title, uh, and also it can't have any weaknesses, like as soon as you admit to a weakness, also no. So we've sort of agreed on these things, and they're just not true for all the research there is. Like there's very interesting research that does not achieve state of the art at all, but just says, hey, here's some different interesting thing, and maybe you only need 4 pages because whatever. Yeah, so I think the uniformity and the convergence to few topics and few ways of going about solving these topics is a bit of a, yeah, it's a bit sad, and hopefully that's gonna come back or change a bit.
Yeah, yeah. So then that leads me to the next point in this direction that, like you already mentioned about some bits, for example, symbolic AI or symbolic reasoning, evolutionary AI, and do you think these are the? I mean, there's already enough focus on these areas, but not enough interesting benchmarks are being broken in these areas. They still fall short, so nobody pays attention.
Mm-hmm.
Um, but is this all you think, or you think there could be other ways? For example, causal modeling. Like we don't understand
Mm-hmm.
what's a causality really, because if there is no confounding factor, then you cannot say what's cause and what's effect.
Yeah, I all of these things are, let's say, they're lagging behind in solving our benchmarks, but they're, I think, just as interesting. Sometimes even if not more interesting. Probably it shouldn't be as much as one field against another, but I think what we will see is sort of a reappearance of, let's say, symbolic AI. I don't think someone's gonna come up with pure symbolic AI that just is better than the neural networks. What we'll probably see, and we already see this to some degree in research today, is that symbolic AI just comes in, and the synthesis of deep learning and symbolic reasoning, the synthesis will be better than just one of the parts alone. So we'd be able to sort of take what is really good about deep learning and take what might be good about the other fields and combine them to build even more powerful systems. And I think, yeah, there is a growing field of sort of neurosymbolic AI, for example. Um, so these are definitely interesting directions. Also, the introduction of causality research to in combination with deep learning, because if you read up on causality, it's always like, okay, we have variable y, we have variable x, and then we have some noise on top of that, right? And then you have the causal graph, and maybe the causal graph has 3 or 4 variables, right? And we're just used to a little bit of a different setting. But I think this is, I mean, this again, this is already on the way. People are doing this, and I'm optimistic that this will bring a richness to the current field if these things become more powerful or more integrated.
Yeah, yeah, I agree. Yeah, I mean, if you look at like at least the causality, every causality paper I read, I always feel that okay, God, if I finish this paper, I will be able to answer this question: is car a cause or is wheel a cause? And it will be clear to me. And it never gets. After reading no paper, it's clear to me what is a cause really. So we artificially say, well, this block of information is a cause. It's entirely a hypothesis. The cause is a hypothesis, and the the effects just fit your cause. But what's the best formulation of a hypothesis? This is so out in the domain of unknown.
Yeah. Yes, and I think so. Just from my impression of, let's say, the causality field, that this is quite a rigorous field. It's quite an academic field, and most results are also kind of negative results, saying, okay, if you don't know this and this and this and this, then it's in fact impossible to figure out the true direction of causality, right? So there are a lot of these results that are very strict. Only if you have all of this information will you even be able to make a causal statement that is provably true. And it that doesn't yet square with, let's say, deep learning. We know nothing about deep learning theoretically, right? We have no clue whether it converges, if it converges, whether it converges to a good optimum or a bad optimum. We have no idea how much it generalizes, right? We don't even have good bounds on that, except extremely loose bounds. So these two worlds are, as of yet, a bit disconnected, and then one wants to make quite rigorous statements about what you can and cannot know and can say, and how much you can say about it, and the other one just goes like GPU brrr, and at the end, right, you get a model out of it. But I'm as I said, I'm confident, I'm optimistic that people will be able to find some synthesis where every all both fields will have to come some sort of a bit of a step to the middle ground.
Yeah, and about symbolic reasoning, would you say that vectorized, like quantized vector, quantized autoencoders, they did a good job of showing that hey, every data can be mapped to like a pre-templated quantized vector.
Yeah, it's an interesting development, right? Because if you think about symbolic reasoning, it's really how you introspect your own brain. Like if you ask yourself, okay, how do I come to some sort of conclusion? How does my thinking process work? I think most people would describe that very much as symbolic reasoning, right? You say, okay, the I have a representation of this object in my head, and then I have a representation of me, I have a representation of door, and then I sort of in, infer what happens if I walk through the door or something like this. It's all very discrete objects that interact with each other, and this this is very naturally, or yeah, how you think of people, how you think of objects is very naturally symbolic. And you can understand sort of the early pioneers in AI that were trying to say, okay, there is a potential that we can solve AI by just making very powerful symbolic engines. Um, yeah, I'm not sure. I'm not sure if that is the case really, because if you go if you again introspect yourself, you might notice, at least I noticed, there is a lot of non-logical stuff going on.
Yeah,
There's
I
a lot of stuff just popping into your head, and you just make kind of connections and so on. So I think that the vector quantized models might be a good place for that, because essentially you have this continuous model, and then at the end you end up with these kind of
discrete.
discrete,
Yeah,
exactly, vectors that kind of bunch together a
bunch
bunch of
together.
stuff, but
Yeah,
then you always have it's still a vector, so you always have the opportunity to
do
sort of
computation.
modify the
Yeah,
vector and so on.
yeah.
Yeah, so
I
it's
actually I remember a personal story like from what you said, that where does these ideas pop up and how it's done mathematically. We don't have a clue. Once I was narrating a
mhm,
story about like some 20 years back, 15 years back in Bangalore, and I wanted to tell a story about a watch, and then I
mhm,
forgot the name of the watch, and from somewhere like my brain told me that try to remember the logo of the watch, and the
mhm,
moment I remembered the logo, immediately the name popped up. So I'm thinking, wait a minute, this watch is first indexed by its name. It's also indexed by
mhm.
its logo. And that logo is also indexed by the name. And brain
Yes, yeah,
also knows this path.
yeah,
So
yeah. It's crazy. Like the yeah,
and like how it has been learned due to some inductive bias or due to some data, well, I don't know. Like that incident only happened once. So
mhm,
so that actually leads me to like some details here. So like the direction of transformers
mhm,
is like I feel it's an interesting one because it shows one very specific property. There was a paper which said that it's called Transformers as Universal Computation Engine.
yeah,
It just came out recently, and they have taken a pre-trained transformer and the language, like kind of frozen those weights, just put another
mhm,
additive layer to do computation on the image. And with few short examples, it generalizes extremely well, and that's what you expect brain to do when a part gets damaged. Then
mhm,
that activity is taken by other parts of the brain.
yeah,
So, like, and you have said this on your show before that you have like you really feel that transformers are universal computation engine, and but there are some detractors saying that no, all you need is mixing. It's not really
yes,
transformers. You just need to a mixing strategy, and transformers just learn one strategy.
yeah,
And there's one more paper that says that attention is not all you need. It's a skip connection that does the job. So, what's your
yeah.
take on this?
Yes, I mean, this is exactly, these are the interesting things that are happening, I think, on a fundamental research level in our field. There are of course many interesting practical things happening around AI, but these developments you've just mentioned. These are things where also, everyone has to change their opinion with what's coming in, with what evidence we get from these new results. So yeah, I've made the point that transformers, because essentially they're a feed forward layer, but the weights can reconfigure themselves every time. So this is a very dynamic computation, and it is the most dynamic computation that we have come up so far with, that is still practical to implement. So I've made the argument that yeah, these are kind of the most general form of neural networks that we have, and therefore, if you have enough data, they should be able to learn the most flexible functions. But yeah, then other papers come in, like MLP Mixer, that essentially shows, look, if I just kind of mix up my dimensions in some way, and the way is really arbitrary, like I just divide images into patches, and I don't even keep the patches at the right place. Like I just make a sequence out
Sequence.
of them, right?
Yeah.
And then I just kind of mix, like I just once I go over the image and once I go over the channels, and that's just gonna be enough. Um, it's astounding. Um, so I think the lesson is still, if you have enough parameters, many things are possible, and and there might be, in at least in the tasks we apply it to, it might be the case that you'd rather go with something like MLP Mixer, because it's just way faster to run than a transformer, because you don't have this dynamic reconfiguration every time. It's just like a really raw forward pass. It's way faster, and it can essentially give you the same performance. So but it's also interesting from, well, like a research level, a fundamental research level, that it seems to be transformers actively decide how information should be routed. That might not be as important, yeah, as you say, as we thought it was. As long as we make sure that information can get from anywhere to anywhere, we might be good. We might be okay. And then this other paper came out. Yeah, this transformers are a universal computation engine, which again raises sort of the question, like, what's going on here? Because they just freeze these whole dynamic layers, like all of the magic layers essentially, and they just kind of adjust the normalization layers, the in between, a little bit, like let's say the glue between the layers. If they adjust that correctly, they do really well. Now, I have to say, I've seen MLP mixer results reproduced. I have not seen yet many successful applications of the universal computation engine part. So in we've tried this actually here with a student, and we have not found um, this to carry over into other domains. So I'm a bit skeptical if that is really sort of a universal effect. But what we might be able to say is that there might be primitives that are just useful for kind of natural signals,
Yeah.
sort of features, and features upon features, just kind of how features are combined, these primitives. And as long as we can adjust kind of how the data is routed through these primitives, we might be fine,
Yeah.
in training good models. So yeah, we learn more and more every day essentially, and I think that keeps it interesting.
Yeah. Yeah, I agree. I mean, like from all of this, I feel that I mean, mixing, like how do you mix information? That is a very interesting part. Do you mix randomly? Do you mix aligned to some objective? And that makes me want to ask you is that, do you think the magic is in like, so the magic happens in two places essentially, either at the input side where they just like do like the best like way of transforming, or the output side in terms of objective. So, d- so do you think the magic could be in the final objective, like this unsupervised pre-training, just mask something and ask the model to predict a span? Like, is it enough?
Yeah, I mean, it's a good question. We have to keep in mind that these results, like, transformers and mixers and so on, they generally are done in really big models with a lot of data, and and that and if you have a lot of data and a lot of parameters, it makes having the correct model architecture just less useful, right? Like, we argue, oh, CNNs are good because they have this inductive bias towards locality, and RNNs are good for this. And then if we have, I don't know, like RepNet, like there's a neural network designed for counting repetitive actions in videos. It's very specifically designed for that, right? And you might argue this is a really good architecture for this problem. And all of that sort of becomes way less important once you go into the I have infinite data and a really large model regime. So um, the magic, I guess, the magic is still, even if we have lots of data and lots of parameters, how does it generalize? I think that's a fundamental question of neural networks themselves. How does anything generalize if we just overfit so hard? Uh, but yeah, I can't necessarily tell you. With respect to self-supervised learning, it appears that how you choose the data augmentations are very important. I think more important than the exact formulation of the loss function. So by constructing data augmentations in a smart way, these self-supervised algorithms seem to get a fairly decent understanding of just what the data space looks like.
Yeah, and there is no theory around it. I mean, at least this will be a step in investigating this. That how these data augmentations shape the manifold. Like, what happens to the manifold suddenly that it's so good at generalizing?
Yeah, I mean the theory people are going to protest that statement. There's a lot of theory going on, but I think it's fair to say that we understand with regard to really the practical tasks that we do, we still understand very little about why anything works or how it affects, as you say, how various augmentations and so on affect the shape of like the data manifold or the weight landscape or anything like this. Yeah.
Yeah. So like that drives me to the next question. It's like that list here. Um, how much do you think we can learn from the brain? Because like I have this like I read something like a couple of months back that till last year they used to believe that one single neuron is not capable of doing a XOR operation. You need a bunch of neurons. Then last year they realized that one axon itself can do XOR. Like,
Yeah.
so it's like a mini neural network. Like one connection is a mini neural network.
Yeah. I'm I've heard this from various places that the the brain itself is sort of a mystery that keeps on giving new insights even now, like even after many years of research into neuroscience, there is still quite little understanding, even at the level of the neuron, as you say. Like I get that we don't understand much of how neurons operate together, and it's very complicated, and everything's connected to everything. But even at the level of the neuron itself, there are so many effects that we don't understand yet. And of the effects we understand, there are so many that don't make it to our artificial neural networks, like things like long-term potentiation and whatnot. Like there's so much stuff that the neural networks we have are sort of, they've been inspired by the brain, but they're really disconnected. And there are multiple ways of getting inspired by the brain. First, you could try to sort of bring in a lot more of these like fundamental neuroscientific recognitions of, let's say, the neuron itself. You could say I'm going to build up my neural network with some sort of, let's say, long-term potentiation as an effect built in, and see what happens. The other way is more on the higher level, where you say, oh look, in the brain there is an entire region that does, or an entire subsystem that does spatial navigation, and there is another entire subsystem that does memory, and there is another subsystem that does something else, time, some tracking time or something like this. Why don't we build AI systems that have the similar subsystems? They can be implemented in deep learning or something. Why don't we have that and then make them work together as the brain does? I think it's a yeah, it's definitely a promising approach. And you always have to ask yourself, um, the human brain and the way it is the architecture we're seeing necessary for intelligence, or is it just, or so is any particular thing in the brain necessary, or is it just an accident of history? Like, could it have been done completely different? And we don't know, because we only have one human brain sort of to look at. We don't have many examples of different brains where we could see, aha, here are the commonalities, and here are, this is just happens to be in this population,
Yeah.
we have no clue, right? So it's very difficult.
But you think like this big limitation. Sorry about this noise. So, so like, do you think this limitation of us that we cannot peek or poke into a human brain will like this will always stay, right? So we will never be able to look that granularly at a living brain cell. It will probably be dead almost. So like we are probably like limited to the second case, like you said that hey, okay, we know that brain does these things. Let's make a set of tasks which are kind of we hope are universally. I mean, every future task is kind of a linear sum of rewards from these tasks, and then you will just learn a universal engine. But what are those set of tasks? There's a theory around that, because I'm going to bring some Indian spirituality here. So they say that like your body is actually a microcosm. Like everything that's out there is in your body, and it kind of makes sense for me. Like thinking that whatever we experience in this body. Even an idea of eating something first already makes me feel thought to map it to my hand, my tongue, and my leg. So there is some quantization. This is the limited manifold of every observation that I have, and I'm going to map everything to this body manifold.
Yeah, yeah, absolutely. Like, if you ask, is there some theory around, what subsystems we should build and how we should connect them? There are as many theories as there are researchers in the field of AGI. Like this, there are researchers in machine learning, and they care about building models and beating benchmarks and so on. And then there is the field of really people that worry about how do we make human level or beyond human level intelligence. So AGI, whatever AGI means in their context, and they all have different opinions about exactly what you're saying. Like, what should we build? How should we go about there? So it's a rich field, and everyone has good arguments, but then again, everyone else also has good arguments. Like, there are people who approach it by saying, there is this set of core knowledge, what they call, like, and we should just have sort of that core knowledge built in, just in whatever way the network, or sorry, the AI should be able to perform these core tasks, or have this core knowledge, because we observe it in all humans. And then other people go about and say, okay, here are the different subsystems that the brain has. We'll just replicate those tasks, as you say, right? We just have those tasks, and every other task is then a combination of those tasks. And then there are so many different opinions on how to go about this. Yeah, it's an interesting field, and you also, what you're saying, it goes into the direction of what's called embodied intelligence.
Oh yeah.
In that you there are a lot of people that are convinced, and they also make very good arguments in that in order to have something like human level intelligence, you have to have this in a human body, or not necessarily a human body, but you have to experience the world as an embodied creature or object in order to really, because as you say, if doing something, immediately you map it to yourself, to your body, to your even abstract concepts. Somehow you are able to act them out. Or so, like, okay, if I describe a manifold, I do this with my hands, and like there's a very intrinsic connection to the physical world,
Yes.
for our intelligence. And a lot of people are convinced that if we want to build such an intelligence, it necessarily has to be connected as well to the physical world.
and and it does give you some kind of regularization constraint also, because now if you're like an all-seeing an eye sitting in the sky and trying to learn about everything, I mean, it seems like it's better to be an embodied entity. um,
Yeah, sure. And I think I mean, this goes also into the theoretical again, but there are results that show that, if you really conceptualize intelligence, as being able to solve arbitrary tasks, then, like, then that's not really possible, because they're like the arbitrariness, like at the same time you'll be able to do everything, but at the same time you'll be able to do nothing
Nothing.
of
Yeah.
usefulness,
Yes.
right?
Yes. Probably constraints make you more intelligent, like kind of.
Yeah.
And and I was not going to ask you this, but because you emphasized, so this idea popped up. I've been thinking about it for some time. Like crows are already so smart. Why do we always think about human level intelligence? I mean, that is so far. I mean, just replicate crows. They just have 2 billion neurons. I mean,
Mm-hmm. Yeah. It's. I think when people talk about human level intelligence, it's both very far away, and also it's like a tiny step if you think of like super duper intelligence, like like a rock is here and then a human is here, and then super duper intelligence is so much smarter than humans. So in the same vein, you can say that's just a tiny step. But I agree. We can't even we can't even rebuild the intelligence of quite simple organisms. And I think people hit the fundamental differences between machines and living things. Uh, and that's not an easy thing to bridge necessarily. Uh,
yeah,
Something like an ant or so, it's incredible. We could never like we have a hard time building robots that are as smart as even a like a single ant. And then you can debate, okay, does the ant actually have intelligence, or is it just reaction? Like I don't know.
yeah. I mean, like, yeah. If you take a crow and you teach and you tell the crow that hey, if you select the cat button or those solve those captures, you will get food.
Yeah,
It will be so good at solving captures. It will just get it
yeah,
better than.
yeah.
So then there's this question that this intelligence is embedded only in head or the entire body. Then
Mm-hmm.
what are the parameters? Is every single cell in your body you count as a parameter?
Yeah.
And then what's the theory of over parameterization? Like,
Yeah, I mean it's an entirely justified question whether or not there even are such a thing as parameters. Like certainly biology doesn't have any like actual floating point numbers anywhere, right? This is all so much more complicated than simply saying, okay, here is 16 bits of information and here is 16 bits of information. um, I think if we'd really want to replicate anything like the brain, we might have to go analog computing and actually, build a brain. Um,
probably because
with
I mean, I certainly can't do floating point because my brain doesn't do it. If my brain interacted with other neurons with floating point numbers, I should be able to do like calculations in my head, but I'm not
yeah,
able to do it. So probably brain doesn't.
mm,
um, I wanted to like tackle two technical questions on this. Like,
mm,
so one thing is active learning,
mhm,
and another thing is learning as much as possible from one sample.
yeah,
So like for example, hypothetically, if we treat each sample as a simulation environment, like an image itself, we treat it's a simulation environment, and then the decoder so encodes itself as a simulation environment and gives reward to succeed, and then the decoder decodes it in some action, and
mhm,
then like from so I'm just saying that why don't we focus on something like so that that can harness the power from small data. You learn as much as possible from one data set without
yeah.
remembering. So that and yeah. So please, your thoughts on
There,
that.
yeah, there are many, exactly. There are many sort of um, definitions of intelligence that target this, saying, okay, it's not about how much I can learn, but it's about how much I can learn given how much data I have. And especially if you look at humans, we're incredible at learning from small data. You
Resource.
have to give a human, what, three examples or so of a new class, or even one example, right? Like someone who's never seen an airplane, you like that's an airplane, and they'll be able to generalize incredibly well to new things. And it's a bit of the question whether you are, or how much you are already pre aligned to do these tasks, like, or how you even do these tasks. But what do, many years, many generations of your brain evolving and forming, how much does that precondition you to be able to learn from small data? And then also, you've been on this world many decades already, and every second you have visual input. How much does that precondition you to learn new things very quickly? And the and the question is, we don't really know the effects of either of those, and maybe we won't find out very soon. But I think, yeah, the focus on small data is definitely something that is going to be very important if we want to extend machine learning to the practical real world, because there are incredibly many domains where you just don't have big data, where you have few samples and you need to be able to learn something from the few samples. Um, yeah, so I think it's very important. I don't know how to get there necessarily.
Yeah, yeah, I agree. And like another like sidekick for this big picture is active learning, that models can
Mm,
choose that I want to focus on this sample because I can learn a lot.
yeah,
So like
that's true. I mean, I active learning is, but this is not. I mean, this is not a controversial opinion. Active learning is an incredibly powerful tool, especially if you think about human machine interaction, right? So I think this is how many people even imagine AI tools to be, or computers in general. Like, you start using it, and then as you use it, it gets smarter, and you only need to interact with it whenever it's not sure about something. Right? I think, you know people almost expect that a little bit. I think, yeah, if you tell people I have something that's intelligent, I think that's what that might be one of the things they expect, right? That they don't have, like, there's not the same error every single time. They use some kind of a program, and like, why can't it just learn what I want?
yeah,
And
yeah,
active learning is I think the technique that's going, like, in many of these areas where humans and AI tools will have to interact. I think active learning must be on the forefront there to make these products better.
and I think active learning will be from both sides. AI will be learning, and humans will also be actively learning how not to interact
Yeah,
because it's not useful.
I mean, this is crazy, right? I so with stuff like Google, it's almost like people have become a, a like accustomed to how to search Google. You don't enter into Google. You don't enter just your whatever you want to know about. You specifically, you filter in your head. You filter the keywords. Like, you think about other keywords, and so the way you phrase, you know, like, sometimes, I type something, and then at the end you just go like, how to, right? Like, so, as you say, this has come both ways. Google has tried becoming better, but also people have
Try to become
adjusted to
Google like.
how I have to query Google. It's
Yeah,
very interesting.
yeah, yeah. I agree. I actually had like one very very generic question, also loaded with
Hmm.
meaning of spirituality, and some very specific questions, and then we are good. So like, what do you think is like the purpose of intelligence? Like, because if people say survival, but
Mm.
bacteria or a tree was doing
Yeah,
fine, there was no need of evolution if that was the reason. So what
yeah,
are we doing here?
yeah. I mean, this is just my guess, right? But I think one of the major purposes of intelligence is probably planning is one, and planning is necessary if you're ecological niche, or if you're an organism that can't afford to die often. Like, okay, you can only die once, but, like, you're, in general, this the representatives of your species cannot die often. So humans, you know, human offspring, we're not super prolific. We're not prolific like bacteria or ants or something. We don't produce incredibly many offspring, and we it also takes a while. Like it takes what 20 years for offspring to become mature enough to produce other offspring, and that's just a situation where you can't afford that people die every 5 minutes. Like it's fine if a bacteria lives for a minute and then dies because it does something stupid, but for a human, you like the species just can't afford that.
But
So
this,
having a planning, sorry.
yeah, so I was just thinking your embodied example before that. This is clearly a problem of being an embodied species because,
Yes.
but then lions, tigers, chimpanzees, like they also had tools for the natural environment to just keep growing
Yeah.
because they still exist. But a,
Exactly. Yeah.
a branch of
I mean,
that,
and they're also intelligent to a degree, right? I mean, it's not well. If you might think further and say, okay, there's also consciousness, like, and it's not entirely clear that um, other species have consciousness, but it's certainly a chimp or a tiger has a degree of intelligence, like it, by many measures of intelligence. These these animals can learn new tasks. They can, they can reason to a certain degree. They can perform some simple logical inferences about what's going on around them and so on. And certainly they can plan, like they can plan ahead, a little bit at least, right? So I think one of the one of the purposes of intelligence is planning. So you plan ahead, so you recognize, oh, if I do this, I'm going to die, and then I don't do it. And there are probably other functions that help as well. For example, um, communication might be an important one. So if I can communicate well, then I can probably organize society better, and that again.
yeah, I mean,
Yeah.
definitely if you can communicate all the past learning that you had from your past species, you can collect and you
Yes.
can transfer. So you increase the longevity. But I had a silly question. Like, if you
Mhm.
like, in terms of intelligence, would you say it's scientific intelligence or social intelligence? Because scientific intelligence can produce atom bomb and then we can kill all ourselves. So our intelligence,
Yeah.
which was supposed to increase our longevity, killed us because. So, would you make a separation, or you would just say that's by hazard that intelligence?
Well, that's a bit of a distinguishing factor between Lamarckian evolution, I guess, and Darwinian evolution, where it's not like it's not necessarily that. I'm saying if you have a million human species on a million planets, some will probably survive for long. Not necessarily all of them.
Yes, yes, and now I have a like really silly question, and then yeah.
Mm.
So like, why do you do you think these tree-based methods are almost AGI of tabular data? Because it is so
So
hard for any deep learning model to beat LGBMs when the data is tabular. So
yeah, yeah, but I mean, the date, yeah, data being tabular though is already a heavy constraint,
inductive
right?
bias,
So,
yes.
right, the I think and that's the whole symbolic AI logic
Yeah.
people and so on. Once the data is in a table, the computers are really good at it. Like, it's like, okay, this column, compare, add,
Yes. Group
inference,
by,
like
yeah.
reason
Yeah.
across it, anything, even learned functions across it become all of a sudden quite powerful on computers. The the bigger question is that most of the world doesn't come to you in a table, and also how the table should be constructed in the first place
Yes.
also doesn't the world also doesn't give you that, right? It's
Yeah.
not even that you it's a problem how to fill the table. It's that you also have to somehow come up with
Yes.
the table.
What's the primary key?
So
What columns stay?
yeah, Exactly, yeah. And I think just recently in some benchmarks on tabular data, neural networks have actually beaten sort of the classic methods. So I definitely agree with you that this might be one of the harder tasks for deep learning, but yeah,
Yeah,
so far we're safe.
yeah, yeah. Well, Yannick, thanks a lot for taking time and spending more than I think we agreed. Uh,
Not a problem. Thank you for having me.
I hope I have recorded this well and I will post it and let's stay in touch. It's super to hear from you.
Sure. Thank you. And I'll send you my recording over.
Thanks, Yannick.
Thank you.
Bye bye.
Bye bye.